Okay. We said we would talk a little bit about Hartronization, and the first thing I want to do is to bridge the gap a little bit between what we did until now and so what the partons do to what the hadrons actually do. And the simplest thing you can imagine goes under the name of local parton-hadron duality. Was it local hadron, whatever. These two commute. I want to remind you of what the spectrum looks like. So the emission spectrum of a gluon looks like dk perp over k perp, d omega over omega. And we know that we need to cut off the k perp at about r. And when we discussed the whole orders summation, I said, well, actually, there's what you would call perturbative gluons, and there's the other guys, the gluers, basically very soft partons, just at the edge of being non-perturbative, and those are the ones that actually make sure that hadrons form. I just borrowed the name from the Russians. And the gluers are those where k perp and omega is about r, yeah, or 1 over r. Yeah, so these are the guys that live very, very close to the edge. Now, let us take a naive look and say, okay, we know that the gluers are formed at times r, where practically all scales for these gluons, formation time, momenta, energies, everything is proportional to r. They are what you would call hadronic gluons. I know what I forgot. Microphone. But I think I talk loud enough that it doesn't matter anyway. Okay, so these gluers live at scales of 1 over r, and if we assume that those are the ones who form the hadrons practically, then we just say, well, we integrate with our k perps from 1 over r to whatever upper scale, and we get a spectrum. And what you see is the spectrum is such that if you say omega, the omega here that I reserved for a gluer, one way or the other is proportional to the energy of a hadron. Let's forget what the factor of proportionality is. Then you see that the distribution of hadrons with respect to the logarithm of the energy is a constant. So they form a plateau. This is the trivial picture. And now, if you make it a little bit less trivial, you ask yourself, what actually happens if one of my sources, say one of the hard quarks or gluons, emits a second gluon, hard enough? Then this other gluon again will start emitting gluers, and with arguments like formation time, hadronization time, you can figure out at what point these two cascades of gluers decouple, so such that you have two jets. You have one jet formed by the original quark and one jet formed by the hard emitted gluon. And the jet internals, the hadrons, basically being driven by the gluers emitted by both. Now, let us see what happens then. So we add this extra gluon radiation. So this is the term that we had before. We basically said we integrate over energy, we integrate over angles. It's pretty much the same as integrating over k perp. And I make sure that the transverse momentum is larger than 1 minus r. But now I add a second radiator. So one of these guys has radiated something relatively hard. And I ask myself, what do the gluers do? And I have a choice now. I can add these two bits in a coherent way or an incoherent way. Or let me phrase it differently. I can encode angular ordering or not. And if I encode angular ordering, The only difference is what I do with theta max. If I add the stuff in an incoherent way, then theta max is 1. It's just the maximal angle. And I say it's 1, it could be pi, it doesn't matter. It's a big number. If I respect angular ordering, then this theta max is given by the theta naught of the first emission. And what I see is two different results. One is basically a logarithm of this guy and a logarithm squared of this guy, which is pretty much the original spectrum. And then you have another one, which is pretty much this guy. If you do the coherent sum, they start mixing with each other. And now you can ask yourself, this correction factor, what does it do? And this correction factor here has the following happens. If you minimize or extremize with respect to epsilon, in that case, you find out that this epsilon, the energy of the gluons, is pretty much like 1 over r. This is where the thing maximizes. And 1 over r is about the mass of the hadrons. So in the naive case, if you do an incoherent sum, practically all your hadrons want to sit energy-wise at their mass. So they're slow-moving objects. And it's not a big surprise because we said k perp, k long, energy is all proportional to 1 over r. This is the edge of the gluers. However, if you take angular ordering into account, the expectation value of the energy of the hadrons scales like the square root of the energy of the system. That's a big difference. And lo and behold, this is what it looks like. If I would plot it as an incoherent sum, at some point I develop this plateau I talked about before. But if I take into account, and the only thing that this incoherent sum does is it shifts pretty much the height of the plateau. If on the other hand I add angular ordering, then I get a maximum here. And this is what people measured. E plus E minus collisions between 14 and 91 GeV. 14, 91. And you see, indeed, the peak of this thing scales like square root of E. So if you want to get hadronization right, under the assumption that the hadrons are where the partons are, then you better make sure that you get the partons right, because there's no way that you will get the hadrons right if you cock up the partons before. It's a non-trivial statement. It tells you, I mean, I can phrase it in such a way that you would say, completely obvious. What this statement does is it says all the relevant quantum numbers, the flow of all quantum numbers at hadron level follows the flow of quantum numbers at parton level. Okay? And that is the non-trivial statement. It tells you if you produce a strange quark, you will find a kaon or lambda roughly in that direction. You won't find it over here. If you find a strange over here and there was something strange over here, like a kaon or lambda, and there hasn't been a strange quark before, you're very, very likely to find an anti-strange particle to make sure that your quantum numbers kind of cancel out. And so if you start building a hadronization model, there's pretty much, let me call it, there's 3 ways of doing hadronization models. One is that you are completely statistic. So you look maybe at your energies and you just throw hadrons. If you don't include conservation of quantum numbers in a meaningful way, statistical models will completely fail. The next model would be that you have your partons and you let them fragment in an independent way. So you take your partons and you turn them successively into hadrons. these models are much better because they allow you to track quantum numbers. So the logic behind them is that you say a quark in Hartronization turns into a meson and a quark of a different flavor, such that you have Q quark going to a bound state of Q bar prime, and you get a Q prime. So let's say you have a quark of flavor Q. You turn it into a meson, but then you want to make sure that your quantum numbers are constrained. This was what I would call the first successful model. The problem it had was that it's very hard to see how the gluons fit. And there's other problems that have to do with the fact that when you go to lower and lower energies, at some point, your quark here will maybe not have enough energy and you have to do something drastic. And then you have to be very careful how you balance stuff across your event. So these are two classes of models that are, let me call it differently subtle, but they both didn't really work. So let us turn to models that actually work. And the first model I want to discuss is the only string model that ever worked. Sorry, mates. Is there a string theorist in the room? Very good. So it's a little bit of a nasty joke, but string theory got developed because of the success of a hadron model. And the further it moved away from hadron models, the less it had to do with reality. It's another way of phrasing it. It's still beautiful, but it's more maths than physics. Physics has to do with data. Okay, so let us look at what electromagnetic fields look like in electromagnetism. And you know this, right? You have a dipole, and this dipole, the field lines of your two poles will fill all space. They will go down in intensity, but they fill all space. The field is, if you give it enough time to develop, the field will be everywhere in the universe. For QCD, it's not quite as obvious. If you have a color charge and a color anti-charge, because the gluons have charges themselves, you can figure out that they attract each other, and you form a flux tube. And in the limit, where this separation is large, the flux tube becomes pretty much a one-dimensional object. And that is called, the string effect in QCD, or the Meissner effect in QCD. You find something similar in superconductivity. So it's very similar, and you can ask yourself what kind of superconductor the QCD vacuum is. So that's for those of you who like to live on the edge between particle physics and, say, condensed matter. This is one of the things that people figured out at some point, and I think it's still kind of cool and exciting. So what can we do with it? The first thing we realize is if you have a string, you have like a linear potential. And that means that at some point, your bound states, the masses of your bound states, will be linear. How does that work? It works that at very small distances, i.e. at large scales, QCD is perturbative, and you get this 1 over R. But then, at some later point, when you start making the distance larger and larger and larger, the flux tube develops, and you get something linear. And in fact, people who do, say, Quaconia models, like charm-anti-charm bound states or bottom-anti-bottom bound states, use a potential that is constant plus linear term minus 1 over R plus 1 over R squared. Crude fix. And you can start trying to fix the parameters by looking at Charmonia and Bottomonia states. Now, yeah. That is a very, very good question. I think this is lattice data, but a number of these states here are actually measured, and they fit. And of course, if you do proper lattice, your potential becomes more intricate. This is really a quick and dirty fix. But I mean, you can see it. It's good enough for governmental work. There's lots of things you wouldn't understand, but the energies you get roughly right. And that, I mean, given the fact that it's such a simple model, I think it's kind of nice. And the only point I want to make is it lends support to the fact that at large distances, the potential is mainly linear. Okay, now let us play this a little bit from a different angle. So why should we care? Why do we want to get it precise? And let me start with a very simple toy model, because we will use such a simple toy model to fix some other aspects. So very naively, hadrons are more or less, hadron production is more or less constant in rapidity before it keels over at some limiting rapidity because of mass effects. It's a very, very crude way of doing it. The humpback plateau is much, much better, but that's a perturbative input to that. The gluers themselves form such a thing. And now you can say, from lab data, we see that the distribution of transverse momenta around the quarks, very roughly speaking, could be fitted with the Gaussian. It's a toy model. It's super duper toy. So what we do is, we say we have a smearing in pt squared with the width sigma that is roughly the mass of the hadrons, give or take. Now, just for entertainment value, let us calculate the energy and the momentum of a jet. So we insert a quark, we let it hadronize, and we calculate the energy of the emerging thing. So what we have to do is we have to integrate over rapidity, we have to integrate over transverse momentum, we have to put our profile function in, and p perp cos y is the energy. And we get lambda sin y, where lambda is the expectation value of this rho. We do the same for the momentum, and we get roughly speaking E minus lambda. Now, if you put it together, you start realizing E squared minus P squared, that the mass of your jet, just for non-perturbative reasons, is of the order of 2 lambda E, where lambda is the expectation value of my Gaussian hadronic scale. What it tells you is the following: if you have a jet with an energy of, say, 100 GeV, and you assume, because we are very considerate people, we assume that lambda is about the pion mass, then you arrive at mass of the order of 5 to 10 GeV. Just for non-perturbative reasons. So you start with a massless quark, you let nature take its way, you let this thing transform into hadrons, and the emerging system has a non-vanishing mass. It scales roughly like, the mass scales roughly like square root of energy, which you know already, because we saw this in this humpback plateau. Funny, huh? So if you have a hadronization model, you have to make sure that you get a distribution of p perp that kind of fits the bill. And one way of doing this, in fact, is taking a Gaussian. I come to that in a second. Okay, so let us take a look at the string model, because I will now use all the ingredients I discussed so far. So the string model says the following: we have this linear potential, and our mesons are massless quark antiquarks that are connected with a string. And what happens is, let us give them a little bit of a kick. They fly away from each other, and they start translating kinetic energy into potential energy. And at some point, they don't have potential energy kinetic energy left, only potential energy. And then they will go back. but then they arrive at this nodal point, and they have a lot of speed, but no potential energy left. So they flick back. So what your mesons do is such a movement. And that is what the Lund people Lund in Sweden called the yo-yo mode of mesons. Now, the fun bit here is the following. If you assume massless quarks, the mass of the meson equals the area that the yo-yo mode covers in its motion. Okay? That's I think that's pretty cute. Now, this was in the center of in the rest frame of the yo-yo, and this is a Tx time versus extension diagram. If you kind of boost the thing, the area remains invariant. So the area is a very, very good measure for the mass of this meson. Okay, so this is the string model for hadrons, and now we turn the string model into a hadronization model. And what we do is the following. We pump energy into the system. We tell our quarks to have much, 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 much more energy. So they go further. What will happen? Suggestions? It will snap, yeah. And what happens at the snapping points? You create a new quark-antiquark pair, and it works because the energy density in your string is big enough that you can turn energy into mass. Okay? Now, there is a mechanism in QED that does that. Have you ever heard of the Schwinger mechanism? Who has heard of the Schwinger mechanism? Okay. So if you haven't heard it, it's not a problem really. Maybe you were asleep, or Facebooking, or watching football. So the Schwinger mechanism is one of the very few non-perturbative results that we have in a meaningful quantum field theory. What it does is it describes the pair creation of electron-positron pairs in a very strong electromagnetic field. So think of something like you produce a standing wave like a laser wave, and you make the energy intensity such that you can spontaneously pair create electron-positron pairs. In QED, that's relatively tricky because the electromagnetic fields are not very strong. In QCD, that's kind of doable. So what is in the string model typically is that you create new masses with a rate that is taken directly from the result of the Schwinger mechanism. And incidentally, it's an exponential in minus the mass squared. And that tells you that you could equally take an exponential in minus transverse momentum squared, put it in on top of that, to give the quark pair that you create when the string snaps a transverse momentum. And that is in fact what is in the Lund model. Yep.
How do you estimate this points when these quarks they get separated from each other and then there is a turnover so that they come again? So how do you
in the hadronization model, in hadronization models, this point is never reached. This point is never reached because the string snaps into smaller parts and forms mesons. So you start translating the energy of the momentum of the quark into mesons. And where the string snaps, you pump a little bit of energy into the snapping quark-antiquark pair and give it additional transverse momentum with respect to the original axis. Yeah?
So I should imagine it more like a
well,
smooth.
for meson model, the turnover point is given by the mass. Yeah? For hadronization models, you never reach a turnover point. You just go. And So this is what the picture would look like. You snap your string here, and then you have this bit, but then you snap a string here. So you move from the edges to the middle of the thing. Let the string snap, and each of these fragments then is made such that it has the mass of the meson that you wanted to have. Okay? So this is the logic with which this model works. It has a couple of parameters. One is the string tension. Other parameters include the way of how you define how much energy of the original quark stays with the meson and how much energy you give to the residual string. So the fragmentation here in this model works like string goes to meson plus string with less energy. And you do it recursively until your string has no energy left. What it does is it starts filling the phase space between the quarks. Yeah, so you have two quarks, and this thing starts filling the phase space in between, but in such a way that the quantum numbers are preserved, because let's take a look. If you snap the string here, and let's say you had a U quark and you produce a strange quark, the quark that goes back is an anti-strange. Yeah? And in that way you conserve quantum numbers locally. Okay. So the beauty of the string model is, and this is why it won against independent fragmentation, it is very easy to embed gluons in it. Gluons are just kinky. Yeah, so you have a gluon and you say, oh, that just means my string doesn't go from quark to anti-quark, but it takes the detour over the gluon. And the harder the gluon, the kinkier the string. And the softer the gluon, the less kinky the string. And then you just play the game and you start producing mesons, so you nibble the string away from both sides. Now this is nice, because if the gluon gets softer, the string, as I've said, becomes more linear, and it does something else. It's another non-trivial thing. Let us compare in E plus E minus a quark-quark gluon final state with a quark-quark photon final state. In the quark-quark gluon final state, the quark is mainly color connected with the gluon, which in turn is mainly color connected then with the anti-quark. And the color flow between the quark and anti-quark is suppressed by a factor of a ninth, at least, because of the color factors 1 over NC squared. If you have a photon instead, the string is directly between the quark and the anti-quark. And you can measure this. You can, in E plus E minus collisions, you can measure where the hadrons are, and you can compare the number of hadrons opposite to either the gluon or the photon. And you see it's a small number over 1. It's something like 10%. You could calculate a little bit more precisely, but that is roughly speaking the gist. And this is something that the string model gives you automatically, because it draws the strings where the leading color connections are. Okay. So the string model is the model that has been implemented in Pythia. It is, I think, by far the most successful model of Hartronization, and I wish I would have invented it. It's absolutely beautiful, and I have absolutely no idea how to beat it. That's why in Herwig and Sherpa we do the cluster model. Tells you something about the psyche. No, I mean, if you have something that is so beautiful and you have no idea how to improve it, you just say, okay, forget it. I do something completely different. I mean, look, okay. Let us talk football. You American guys can't play football. That's why you invented American football. You pretend it's the same by giving it the same name, but obviously it's a completely different game. And you made a little mistake because you actually didn't even steal it from football, you stole it from rugby. Okay, so that is roughly speaking what we did. We couldn't do football, so we did American football. It's a little bit more brutal. So the assumptions that go into that are a little bit more brutal. That's why this analogy actually works better than I thought when I started it. Okay, so the logic here is the following. Our Partron showers are typically leading, an approximation of leading color. So in our Partron showers, we assume we have infinitely many colors. So every color has exactly one anticolor. This is one of the things that make Partron showers so beautiful. So we have what you would call planar diagrams only. And you can show that this is the leading contribution, vada, vada, vada. Let's not go there. So what it means is that, let's say we have a complicated radiation pattern, but in terms of colors, we know exactly who talks to whom. In the string language, we would now draw a string. In the cluster model language, we say, well, actually, we do something really nasty to the gluons. We split the gluons into quark, anti-quark. So when the Partron shower ends and hits the infrared cutoff of 1 GeV, we stop the Partron shower, and then we do something drastic. We let all gluons split into quark, anti-quark pairs. And that means, if this is a quark, this gluon will split into an anti-quark and a quark, and the anti-quark will have the color that the anti-color that compensates this color. So after doing this, in a first step, you have colorless objects, quark, anti-quark, quark, anti-quark, quark, anti-quark, quark, anti-quark. You have colorless objects and you say, well, actually, these guys are just like mesons. Now we know mesons are discrete states. Some of our clusters will be in a mass range of these discrete states. So let's say if this cluster is very close in mass to pi in mass, we exchange a little bit of energy in our gluon splitting because we can do that. It's a non-perturbative gluon splitting. We can do whatever we want anyway. It's non-perturbative, right? It's game on. That's why we wear helmets. And so we shuffle the energy a little bit to make sure that this thing that was very close to a pine actually sits on the mass scale of a pine. And if it's heavier than the heaviest object that we have, we say, well, then it's somehow in the mesonic continuum, and we just let it decay down. So it's a brutal model. And in its simplest form, the massive mesons would just decay isotropically. We started realizing that this is not so very good because it prevented us from getting the leading hadron spectrum, so the spectrum of the most energetic hadrons, right? So we kind of start making the split, the decays of the clusters a little bit more asymmetric. But okay, it's duct tape, right? It's just patching up something that maybe isn't so patchable. Okay, this is what I just said. Now there's there's one thing that is probably kind of nice. If you run your Partron shower and you form your clusters and you just plot the mass of the clusters, you find out that the mass distribution of the clusters is completely uniform after the shower. And the reason for that is the Partron shower is a self-similar Markovian process. So the Partron shower washes out the information of the high energies. And that actually is very, very good because this is the reason why we can tune our models. So if we wouldn't have the Partron shower and would just say, okay, we produce 2 quarks and we let them hadronize now, we would have a logarithmic dependence on the energy of the quarks. And that means things like string tension or cluster mass splitting variables or so would have to be adjusted for every new process. But because the Parton Shaw is self-similar, we know that once we run the Parton Shaw, what comes out as a Parton ensemble locally looks the same, irrespective of the high energy process. And that allows us to fix they're essentially unphysical because it's just models. This allows us to fix the model parameters at the best data we have and have hope that we can port it by far and large to other processes, to other colliders. And this is kind of important. Now, there's one question that I missed, is how do you do baryons? You said you have only colors and anticolors, but baryons are 3 quarks. And oh boy, we do something really brutal. We invented something called, or we used an invention of something called diquark. So we bind together 2 quarks, and we know 3 quarks make a baryon. So 2 quarks, which are in a color sextet state, in the large NC limit, act like an anti-triplet. If you do Young tableaus, you would see that. It's a little fun bit. So we bind 2 quarks, they're color sextet, but in the large NC limit, they're exactly an anti-triplet. So our baryons are mesons of a quark and a diquark. And that means we let our gluons at some point, and that is where models differ. We let our gluons also split into diquark pairs. Herwig, for example, only allows U and D quarks, and I think recently strange quarks. So there's a couple of differences in how you deal with stuff. Baryons is one thing, heavy quarks is another thing, how you deal with spin, etc., etc., etc. And all in all, this leads to the fact that you have lots of parameters. So the first parameter is you have to have the kinematics of your string or cluster decay. And that is typically between 2 and half a dozen parameters. And mind you, there's no first principles theory for us. Then we must, when the string pops or when the cluster decays, we produce quark-antiquark pairs out of the vacuum or out of the strong field. Which quarks we pop, in which flavor state, at which spin state, do we suppress strangeness, do we suppress diquarks, and by how much? Another 2 to 10 parameters. And then you have your stuff, and you have to ask yourself what mesons to actually produce. And if you do it too naive, you don't get the pi into proton ratio right. So what do? You fix it. Another parameter. So in the end, if you're lucky, you end up with 6, 7 parameters. If you're unlucky, you have the order of 20 parameters. And these parameters have to be fitted to data. So the reference data we take is lab data. And we have of the order of 50, 60 observables. So we have about 30 different parton yields. And then we have all possible kinematical distributions. And if you play the game, you typically get everything done within 10%. And then we send a little prayer, and we say, oh, LHC will do exactly the same. But there's a problem, and I think it's important to be aware of that. By far and large, this works. But when you start looking in a little bit more detail, you start realizing lab is pretty much driven by the quark-antiquark pair you produce in the beginning. So lab fragmentation, to a large degree, is quark fragmentation, and your sensitivity to the details of gluon fragmentation is not so fantastic. LHC is a gluon machine. So there is room for improvement. The other reason why life could be kind of a little bit tricky here is, in the case of LHC, you have sources of color with practically infinite energies. you have your beam remnants, and typically, I mean, if you look at LHC, you have beams of between 3.5 and 6.5 TeV. You may suck out a quark, say with 1 TeV. You still have 3, 4, 5 TeV left over of a quark, sorry, of the proton remnant that acts as a color source. And that means the forward region is a situation with very, very intense color, and this is something that we typically don't see at lab. So the fragmentation of the beam remnants, this is where you really have to pray that our models do the trick. And I'm willing to bet that they don't. But then no one measures it in the forward because this fries the detector, so pa. No, but it's interesting when you do, for instance, when you do astroparticle physics and cosmic rays. Then we have to discuss the beam fragmentation, and this is one of the reasons why typically Pythia doesn't do as well as other codes. It just has to do with the kind of data. Pythia is for that kind of physics a beautiful tool. Okay, very quickly, just for 5-10 minutes, because sorry. Well, the kinematic range of LHCb is pseudo-rapidities up to 5. For Atlas and CMS, it's also up to 5. No, it's 2 to 5. So the difference in LHCb is when you look at the trackers, so the silicon for the charged tracks. In run 1, Atlas and CMS stopped at 2.5, and LHCb actually did 2 to 5. So their overall detector has the same coverage, but in LHCb, this coverage is also for the trackers and for the muon chambers. For Atlas and CMS, they didn't dare to go that far, basically because of the intensities, and the silicon trackers would fry. LHCb doesn't take the full luminosity, so the energy deposits are much less severe, and that's why they can pull the trackers. For the H-cal, it doesn't matter, because the H-cal is just a clump of metal. Yeah, so you can't really fry it. Okay, probably you can, but you can kill everything if you want to. If necessary, you take a nuclear bomb. Okay, but that's why at some point, when we start pushing, so for instance, for this 100 TeV machine, people discuss to go with ETA even further, with pseudo-rapidity even further. At some point, you can imagine that our detectors become sensitive. And one of the things, just to follow this up, one of the things that no one ever did was to try to fit a Hartronization model to Hera data, where you actually have acceptance and sensitivity in a region that you don't have here. Yeah. Okay, multiple parton scattering. I try to explain the simplemost model, and that goes really quick. The logic is the following. Hadrons are extended objects. You have no guarantee for having only one scatter. So everything we discussed till now had to do with factorization, which is what we introduced in the first lecture. For all of our perturbative QCD knowledge to work, we assume factorization. However, factorization assumes that you have in your proton-proton collision only one parton extracted from each of the two. So you have only one scatter with two incoming particles. Now they're extended objects. No rule that there can't be a second one. The description of the second scatter is beyond factorization theory, so you have to model it. What you can say already is, if it has anything to do with perturbation theory, I mean if it follows even remotely perturbation theory, you would assume that the secondary scatter typically prefers to be soft. It's a slightly different version from the omega over omega, dk perp over k perp. The reason underneath is that the simplest thing you can do is a gluon exchange. The gluon exchange diagram goes with 1 over t. If you square it, you have 1 over t squared. T is the transverse. T can be related to the transverse momentum of the outgoing objects. So you want the transverse momentum of the outgoing objects to be small, because then the matrix element explodes. So most likely, most of the secondary scatters are at relatively low PT. Okay, this is what you would assume when you do a perturbation theory. Now, let us discuss the first experimental evidence that such a thing even exists. And pretty much the first experimental evidence was at the Tevatron, where people measured a photon plus 3 jets at ridiculously low energies. So they took jet energies of the order of 5 to 7 GeV, pretty much next to nothing. That is really optimistic. However, then they paired up their jets in such a way that they said, okay, we look for the pair of jets and the pair of photon plus the third jet that are maximally PT balanced. So you pretty much look for pairs that are as much back-to-back as possible and compensate each other as much as possible, because this would be 2 independent 2-to-2 scatters. Yeah? A 2-to-2 scatter, in a 2-to-2 scatter, the transverse momenta must compensate each other vectorially because of in the transverse plane, because of transverse momentum conservation. So if you have 2 scatters, if you want to be sensitive, you look for your 2 pairs to compensate each other. And people measured the angle between them. And it turns out, if instead of having 2 2-to-2 scatters, but 1 2-to-4 scatter, this angle is pretty flat. And then they measured something that was not flat and said, well, actually this bit here, this is the second independent parton scatter. Now, the model that people use experimentally, and this is about 25 years old, maybe even older. The model people use is, they say, well, actually the cross-section for double parton scattering is the cross-section for the individual parton scatters divided by something with the dimensions of a cross-section, with the dimensions of an area, and they call it sigma effective. And then you can use sigma effect, then you can use these plots like this to fit sigma effective. Sure.
You say that Carlo uses non-IR state.
Mm-hmm. Yeah. Uh-huh. Careful. Yes. Yes, very good. Yes, one should definitely be very careful. No, but we did the same stuff now a couple of times at the LHC in a proper way. So so the first measurement of double parton scattering at the LHC was a measurement of W plus 2 jets. And so you have a direct component, like a 2-to-4, where you produce the W and the 2 jets in one scatter. And you can also just have 2 independent scatters. And the observable that proved to be the best one was something that is like the vectorial sum of the 2 transverse momenta of the 2 jets normalized to their scalar sum. So it's something that looks like P perp 1 plus P perp 2 divided by the absolute values of each, up to a factor of 2 or so. So this is the observable here. And green is the measurement. The dotted curve here. So what you would assume if you have double parton scattering, because they compensate each other, that double parton scattering lives relatively close to 0. At 1, the two jets point into the same direction, pretty much. And that is definitely not the double parton scatter, so that is the direct component. So you do the fit, you do the best you can do for the 2 to 4, and then you fit the residual thing. And the beauty is, you can, for the residual thing, for the double parton scatter, you can either run a simulation, or you can say, well, we take actually W events as measured and overlay them with dijet events as measured. So we can basically check our theoretical prejudice by directly looking into the data. And if you get the same results in your fit, you are fairly confident that you didn't botch it up too badly. So this was the first measurement of that kind. And what you see is the screen measurement that I showed you. This is the gamma plus 3 jet. That was the first halfway meaningful measurement. And you see, when you measure sigma effective and you just take all the measurements face value, which you maybe shouldn't do or should do, what, as a theorist, what do you know about the quality of the measurement? It can either increase logarithmically or it can be a constant. Yeah, so if you do more measurements, you will, at larger energies, we can maybe see if there's a logarithmic increase with energy or not. Okay. So very quickly, underlying events, same story as before. So what is the origin of multi-parton scatters? The origin is kind of a funny one, and you have to, it's nice to see that. So when you calculate the parton-parton cross-section with respect to p perp, and you integrate it over p perp with respect to a p perp min. So you calculate quark-quark going to quark-quark, quark-gluon going to quark-gluon, you sum them all up, and you integrate them over available phase width with respect to minimal transverse momentum of the outgoing partons. You get a number. And then you can compare this number with the total proton-proton cross-section, or with the total inelastic proton-proton cross-section. Doesn't matter. This is the same by a factor of 2. The point I want to make is, I can choose p perp min so small that it's larger than the total pp cross-section. And it works because the sigma by dp perp diverges for p perp going to 0 because of the T-channel gluon exchange. Now, what is the physical interpretation when this becomes larger than this? So if the cross-section for constituent scattering is larger than the cross-section for the process, it means you have more than one constituent scattering. It's the only way you can square it. It's a requirement of unitarity. So basically what it means is you have your cross-section, and this is pretty much, this is the limiting cross-section for a single parton-parton scatter. If you start exceeding it, you must have more than one. A black disk cannot be blacker than black, because you can't improve on blackness. Okay, so this already tells you how practically everyone simulates multiple parton scatters. We just take ordinary 2-to-2 scatters, we allow transverse momenta to be really low, and we distribute them in such a way that you get a Poissonian distribution of parton-parton scatters with a mean that is different from 1. This is pretty much in Pythia, Herwig, and Sherpa. There's other models which use Reggie theory, but I don't want to discuss that. Yeah.
How the PP cross-section and total cross-section has been measured?
How it has been measured?
Yeah.
The simplest measurement, or the simplest measurement strategy, is to use something called the Optical Theorem. So unitarity of the S matrix tells you that there's a connection between total and elastic cross-section. So what people do is they measure the elastic proton-proton cross-section with respect to the momentum transfer and extrapolate to momentum transfer 0, where you can't measure, because if you have momentum transfer 0, the protons follow the beamline and you can't have a detector in the beamline. So you try to put detectors as close as you can to the beamline and measure protons. Okay? I think the experiment that published most of it is called Totem, and they have detectors called Roman pods that are 250 meters or so down the beamline on both sides, and then you try to do your extrapolation. And you arrive at something of the order of, for LHC, the total cross-sections of the order of 100 millibarns. The inelastic cross-section is about 50, the elastic is about 25, and diffractive cross-section, where one or both protons just wobble a little bit, is the other 25. Roughly speaking, numbers. Okay. So this is where we are with the underlying event, and now we can discuss how we distribute these guys. Do we assume that the protons, when they collide, have an impact parameter such that you have a different matter overlap and therefore different numbers of parton-parton cross-sections because you have different matter overlap? Which value do you take for p-perp? You can ask yourself, what do you do with the PDFs? One of the things that we all do is we assume that a PDF for a proton minus a parton is the PDF rescaled. Not necessarily a smart idea, but hey. We start realizing that alpha S, when we let PT go to very small values, behaves a little bit shitty. So, and this 1 over PT squared that we have in the d sigma is also not nice. So instead of doing a 1 over PT squared, we do something like 1 over PT squared plus some cutoff parameter. So we try to make things nice, but this means you have a proliferation again of parameters. And then again, you fit to data. So the one thing that is important to realize is when you do the simulation stuff, there's lots of things we know, and we understand qualitatively and quantitatively. There's some things that we understand at least qualitatively. So I think our Hartronization models, there's some physics intuition in it. And there's other things like the underlying event where we are driven by a lot of hope. We pretty much parameterize the lack of quantitative knowledge by throwing more parameters. And so depending on which kind of person you are, you try to have as little parameters as possible or as many as possible. The reason for having as many parameters as possible is that you want your Monte Carlo to fit the data as well as as best as it can. This will help you if you want, for instance, to unfold detector effects, because then the description, if your description is maximally good, you have a chance to understand your detector maximally well. On the other hand, if you have too many parameters, you may run the danger of obscuring the underlying physics. So you have to make a judgment call. And I think the fair statement is that Pythia is pretty much driven by describing data as best as you can, with a lot of intuition when it comes to model building. Herwig and Sherpa are a little bit more in the other side. We are maybe a little bit more extreme than the Herwig guys, so we want to have as few parameters as possible. So we still have about 25 or so, but we don't have 250. So it's a judgment call of how much you want to push it. And pretty much everything that has to do with soft QCD you can capture with a parameter, right? Every new effect, new parameter, no problem. Okay. So this is where we are. So the summary of 5 lectures, and I think that's a very good one. you have to accept your limitations. It's very important to have the wisdom to understand what you can, what you can't do. However, you will never know what you can't do before you fail doing it. Okay? It sounds very silly. I think the one thing that I want to say is so QCD as a theory is a real challenge. We have a beautiful quantum field theory, and the very moment we want to confront it with data, we have to put up with a lot of dirt. And guess what, guys? If you do neutrinos or dark matter or so, at the end of the day, your detectors are made of hadrons. I don't have to say more, huh? So even if you're completely not interested, and this is perfectly fine, at some point you will rely on people to calculate hadronic matrix element, hadronization effects, or other stuff. And if you don't understand that there are subtleties, I think you will have a hard time being as successful as you can. So even if you never want to touch QCD, because I was very, very successful in putting you off. But whatever, QCD is a good thing in that respect, that because of its rich phenomenology, there's many things that we don't understand, and we can try to push it in many different ways. And I think this is something that will hold true for everything we do in physics, and especially in particle physics, in the next couple of decades. We reached a point, I think, where any further advance will come only if we pay in pain, in the pain of calculating stuff, in understanding stuff. It sounds very nasty, but I'm German, so I'm allowed to do that. So, yeah, spread your wings and stand up again. Okay, I said that we run Monte Carlo just for entertainment value. I try to show you what it looks like. So I think I have to. No, I have to go here. I have to do that, and then I have to do this and move it here. Now, if I do, what happens if I do? That is nearly beautiful. Okay. So the first thing I want to show you is a run. So I show you the run card of our code. And we go through it very slowly. So there's a couple of things we're going to do. 1 million events is a little bit optimistic. We won't do 1 million events in 10 minutes. We will maybe do a few thousand. This error is an integration error. It means nothing because we typically integrate for 2% or better. We don't do multiple interactions at that point because the preparation would take 5 minutes. We do set scales, factorization, randomization scale, and the scale at which we start the parton shower. I'm very happy to discuss the scale setting prescription at some point. Let me just say, for the process that we have here, the scales are typically driven by the transverse mass of the Z bose, so we do trillion, or the transverse momentum of the jet if it exists. We will calculate trillion. I show you this in the process in a second. We will calculate trillion and trillion plus one jet, and we will put it together in a consistent way with multijet merging. I didn't discuss multijet merging yesterday, but if you would ask me what was the best achievement of your scientific life, the best achievement of my scientific life was working out how to do multijet merging at leading and next leading order, and that is at the moment. Different codes implemented it. I think in our code we developed it. This is at the moment the precision standard for LHC simulation. So that's kind of, yeah, it's kind of cool, I think. So if you want this explained, I'm very happy to explain because I could talk about it for days. So I didn't even start. In our code, we have 2 matrix element generators. So we have 2 submodules that calculate Feynman diagrams in different ways. So one does it by producing Feynman diagrams, and the other uses Dyson Schwinger. And so our code chooses which one it likes better. we exclude taus from the lepton container. 2212 is the particle data group ID for protons. I could explain to you why it's 2212, but hey. Beam energy is 6,500 per beam, and we switch on analysis code called Rivet. Now the process we look at is we have a container for all massless partons, 93. So we do 93 pair of massless partons going to a pair of muons 13 minus 13 plus an extra parton. Second order in electroweak. We wouldn't have to do this for this process, but sometimes it's good to be precise with the orders. We don't specify the QCD order because it can either be 0 or 1 because of this extra jet. We merge the two samples, 0 and 1 jet, together at a scale Q cut that I said above. Now, this is where it becomes a little bit more interesting. If you produce two muons, we assume the muons to be massless because we are lazy. But that means that you have a divergence in your matrix element, namely 0 mass of the muon pair. And that would be bad because your cross-section would explode. So we constrain the mass to be between 66, which is mass of the set minus 25, and the upper limit is the center of mass energy. And then we say, okay, as an analysis code, we take some published atlas analysis. Yeah, that is pretty much where we are. I took only 1 jet. If I wanted to bore you to death, I would write 5 or 6 here, and we would integrate for half a day. But that's maybe not so much fun. So let us start this thing. So now we start integrating, and it's just a little bit of Monte Carlo integration. So this is the first process. You see every 10,000 Monte Carlo integration events, you see a little bit of result, and you get a total result. And we for the core process, we typically want to have it at 1 per mil accuracy, and we have an expected efficiency of 13%. So 13% of our events would pass unweighting cuts. Now we calculate the same thing with an extra jet in the final state. So instead of 2 diagrams, you have a few more. Takes a little bit longer. Now, typically, we like to have integration results better than 1%, but our code will not stop at 1%. Because we are Germans. We like it precise. So what happens now is the following. When we integrate, we typically translate every matrix element in one specific phase-space mapping. For this process, there's only a few matrix elements, so there's only a few phase-space mappings. If you have a process like production of a Z boson plus 5 or 6 jets, you have shed loads of these guys. And we distribute, we construct our phase-space integral by picking one of these mappings, producing random numbers, using the mapping to map random numbers onto 4 vectors, and calculate the matrix element. And we optimize which integration channel we take consecutively. So it's called multi-channeling, and those of you who do multi-parton final state calculations know how this works. So we automated this because setting it up by hand every time is really boring. Now, at some point you start realizing that you run into the statistical limit, and that's a little bit boring as well. So we thought, wouldn't it be fun to have the 10 best channels and select them and kick out all the others and take only the 10 or 15 best channels and give each of them individually a Vegas for additional optimization. And this is pretty much what happened. And then you get, once you have your results, you can start generating events. Now, if I run again, just because I can, we just look up the results now, and we generate events. Lots of them, relatively fast. At that stage, because it's a really simple process, typically we spend, I would say, half of the time, or more than half of the time, in Hartronization, hadron decays, and analysis. So in all the boring stuff. Once you make your process more complicated on the parton level, you start spending more and more time in the perturbative bit, and the non-perturbative bit stays relatively speaking the same in terms of the time budget. So if you go next to leading order, which we could, it would take more time, but you have higher precision. And I took pretty much the cheapest possible thing that will look roughly acceptable. Okay, so let us take a quick look at what it looks like. I have absolutely no idea what it looks like, to be honest. So that's going to be a fun one. Already there. Okay, let's take D01. Come on. X01, Y02, PD. Let's do PNG. Maybe that works. Aha. Okay, so let us do this a little bit smaller. That didn't really work, did it? Come on, don't let me down. And we do fit page. Okay, so this is a relatively trivial observable. It's the number of jets that comes with the set. And you should be aware, we inserted a leading order result for Z plus 1 jet. We did not insert anything for Z plus 2, 3, 4 jets. This is done by the parton shower. And as we discussed, the parton shower is this d omega over omega d k perp over k perp. But if your jets are hard, the parton shower does not necessarily fill the phase space for two reasons. A, because of divergences, and because B, if you want to make extra jets, the best way to produce it at the LHC, when you produce a set, is not to have final state radiation, but to have initial state radiation. The reason is, your final state radiation may be a gluon of 100 GeV or so. In your initial state, you have a reservoir of protons with lots of energy. And that allows you to suck energy out of the PDF. And this is something the parton shower is not really good at. So it's very good at dressing up everything that goes around the beam, but having something that is far away from the beam, like a jet, the parton shower doesn't do very well. Because that opens phase space that wasn't there before for the parton shower because of the maximal scale. And that's why we start keeling over. I can assure you, had I put higher orders, these guys would go up. And I can also show you, had I done next leading order, this would have been pretty much on top. Okay, so this is the kind of stuff you get. Just for entertainment, I want to show you just one event, what it looks like. So we go through the event. The first thing we find is we have bunches incoming and outgoing protons. our code would in principle allow you to look for photons being emitted by the protons and doing their thing, but okay, we do QCD, so I thought it's not so interesting. Then we see how the first proton splits up into, maybe I can I make this? Lovely, this is much better. So the first proton splits up into gluon, diquark, quark, and the second also splits up in gluon, diquark, quark. The signal process, the one that created the muons, was DD bar going to muons. But then we already also had a little bit of parton showering. So you see a few gluons have been produced in the final state. They hit then we have a little bit of QED radiation because our muons really love to radiate photons. And then we take all our quarks from the process plus from the beam remnants, stuff them into one big blob and turn them into primordial hadrons. And you see we get lots of things that no one ever wanted to know that they existed. So H1 1170, great friend of mine. So we have to let them decay. And just because, it's one of the things that you have to do. If you write a Monte Carlo and you create an H1, you have to let it decay. Now, here's the glitch. Naively you say, not a problem, we just open the PDG. If you open the PDG, you will find out there's not a single particle where the branching ratios add up to exactly 100%. So, what do? If you're very close to 100%, you just rescale. All these branching ratios come with errors. Yeah, so if we are within errors, we don't do anything. If we do, say, B mesons, only about 50–60% of the branching ratio is known. And lots of the stuff is B going to shitloads of pi's. So what we do is, we go back to the parton level, let the parton shower run, hadronize the stuff, and live off and pretend nothing has happened. That works, sort of. And then we have cuties like 1170. You open the PDG, and it says, decay into 2 pions, probably dominant. Decay into whatever. So you see, in the PDG, you see entries like dominant, seen, maybe seen, not seen. And then you sit there and you have to translate it into percentages. So what is the dominant percentage? On a Monday, I think it's 50%, whereas on a Tuesday, it's more like 70%, because I start becoming more and more lazy as the week progresses. At Friday, it's certainly 100%, because it means I don't have to introduce other decays. So a good fraction of our code is decay tables. So we made our own particle data booklet. And in contrast to the particle data booklet, we also give information what matrix element we use. Most of the time we just say isotropic because H1170 doesn't deserve any care. I don't like it. But for B decays, we use form factors. So we have lots of work in form factors and this kind of stuff. And that makes creating such a code at some point really unglamorous. And that is the moment when undergrad students come in really handy. They don't know what they ask for when you tell them, look, you could implement a couple of form factors for hadron decays. It's kind of interesting, and it doesn't even hurt. Okay, so you go through these things, and you see each of them is created in vertex 8 and then decays into one of the next vertices. So here's an A1, cool particle. It's like a friend of H1. I don't like the family. It decays into rho and pi. With the pi, you're happy because it doesn't decay further, but the rho is kind of insistent that it doesn't want to be stable, and so on and so forth. So this is one event. Still scrolling. It's still one event. And it's only the hadron decays.
Each column is for momentum and other characteristics of it?
Exactly. So what you have is part particle status decayed or active, particle type. And we leave a little bit of space here because some of these guys have really long names. Particle number, vertex it was created, vertex it decays, 4 momentum squared, mass, colors, and the decay vertex has a position. Yeah, but you want to have the position, you want to know the position because for B mesons, for example, you have displaced vertices, and your analysis wouldn't work if you wouldn't resolve how far the stuff flies before it decays. Yeah, and so for some of the things, well, we give some information of how off-shell particles are because we do some bright weakness mirroring on top. So it's still the same event. I mean, still. Nice, huh? Funny, I don't know. For trillion, my feeling is probably if you count the photons, I would expect it to be of the order of maybe 100. Because you have. Yeah, because you have as many. Look, you have lots of pi zeros which decay into 2 photons. So my feeling is charge tracks probably of the order of 25, slightly above lab I would expect, but neutral stuff quite a lot because of the photons. Okay, so you see, if I scroll it very slowly, it takes 54 seconds. And then I only produce 1,600 events per day. But you've seen if I don't do anything silly, trillion is really quick. A million events, half an hour or so. So that doesn't hurt. And trillion is one of the things we would use to tune our Monte Carlo. So being relatively fast is not bad. Okay. Do you have any questions left? Yes, no, maybe? What's Yep.
Effects like mistagging,
Mm-hmm.
energy effects, which you probably all should take into account, either via full simulation with G4 or with Gauss and stuff like that.
Yeah.
Take this into account.
No. No, for a very simple reason. In Rivet, the data are unfolded. Yeah, and I have to say I know everyone does it now, but I'm not a big fan of using fast detector simulations. There's a fine line between being a pheno person and being an experimenter. And I don't know the detector, so I have absolutely no idea how I can validate the goodness of Delphs. And that tells me that all the statements I would make would come with a lot of hope from my side, and I don't like to operate like this. I know that many people do it because it sounds nice, but I don't think you generate any more knowledge. So the tool of choice that most people use, and they want to compare Monte Carlo and validate their stuff and tune, is an analysis suite called Rivet. And just to give you an idea, so in Rivet, Atlas and CMS. Oh God, let's do it differently. Atlas and CMS have implemented the analysis code plus the unfolded data that you would, for instance, find in HEP data. What did I do? Silly me. Analysis. So this is about the number of Rivet analysis just from Atlas. Similar number of CMS. So similar number from lab experiment, lots of Tevatron. So we have of the order of 500 analysis in Rivet. that capture a lot of stuff. Okay, and it's a nice tool because yeah, it pretends to be like an experimental analysis code. More question? Yes, no, maybe. What's the score?
0-0.
Oh, shit. Okay, good. Okay, that's it for today, huh? Thanks a lot.